Welcome. Today we shall learn about a few pressure measurement techniques which are used in the natural gas industries. In this particular lecture, we shall be learning about what is pressure, the fluid pressure, the various pressure measuring methods related to natural gas, and then something about manometer, then some pressure transducer. Now first let us come to the pressure. Now as we know, the pressure is the force exerted by a substance. The substance may be a solid or a fluid on an unit area of a surface. So the SI unit of pressure is Pascal, which is also the Newton per meter square, and it is given in short as PA. And pressure represents the energy that a system has to do some work. And we know that there are some various equipment like compressor. Compressor takes in the pressure takes in work to generate the pressure, whereas turbine reduces the pressure and it gives out work. So there everywhere we find that the pressure changes across a compressor or a turbine either to consume the work or to generate the work. Then we need to monitor the pressure in a system so that the system can be operated safely and without any leak whenever we are talking of any kind of storage or transfer. So whenever we are designing any kind of storage or process vessels and transfer lines, we have to take care of the pressure inside the things, because in the storage vessel, for example, if the pressure suddenly goes up beyond the design pressure, it may lead to explosion. And in the process vessels, many times we are carrying out some kind of reactions on some kind of separations in process vessels. So we have to keep monitoring the pressure inside the vessel, because for a particular process takes place at a particular operating condition, and if the pressure fluctuates, if the operating conditions goes away from the designed operating conditions, then we will not be getting the right performance. So that is why we need to be very careful about the pressure inside the system, and so we need to have some appropriate pressure measuring device. Now let us look at what is fluid pressure. Now fluid pressure is generally represented with respect to some kind of datum pressure, and when the datum pressure is the atmospheric pressure, we call it the gauge pressure. And so we have this thing that absolute pressure is equal to the atmospheric pressure plus the gauge pressure. The gauge pressure may be positive or negative, and if we have negative gauge pressure, we call it vacuum, and this can be demonstrated from this particular figure. Here what we see, that there is this atmospheric pressure and there is one point A. The point A has a pressure which is higher than the atmospheric, and here we call it Pg, and the absolute pressure is the P atmospheric plus Pg, where Pg represents the gauge pressure. And somewhere near the bottom we are showing some kind of absolute pressure, that is zero pressure. And we can have various types of units for that. Here we are showing atmospheric, atmosphere, bar. There are various kinds of units, sometimes represent pressure in terms of the millimeter of mercury, sometimes in terms of inches of mercury, millimeter of water, inches of water column. So there are various types of units that are there for the pressure measurement. And here in this particular figure we see the vacuum pressure. Again we see this is the atmospheric pressure, and this P vac represents the negative gauge pressure or the vacuum pressure. So the absolute pressure is equal to the atmospheric pressure minus this negative gauge pressure or the vacuum pressure. So this is the absolute pressure. So this is the vacuum pressure, and this is the more than atmospheric pressure. Now we shall be looking into a few types of the pressure measuring devices which are related to the natural gas processing. So broadly, all the measuring devices for pressure are divided into two types. One is the liquid column measuring gauges, and there is the pressure transducer. Generally, the liquid column pressure gauges incorporate some kind of fluid, and this particular liquid column pressure gauges is also called manometer, and there are various types of manometers available depending on the pressure ranges we need to measure. The U-tube manometer is very common, and in the natural gas industries we use the U-tube manometer because of the large pressure differences we find in the pipelines or the storage vessels. So let us look into the manometer. First, let us see that what it represents. The manometer can be used to find out the pressure difference between two locations, or we call it the differential pressure. A manometer may also be used to find out the absolute pressure in a given system by exposing one of its limbs to the atmosphere. So we will see that in our next slide how it's placed. Now, as I told you that we use different types of manometric liquids like mercury, water or alcohol depending on the pressure difference expected. So we use generally heavier liquid if the pressure difference is large. If the pressure difference is small, then we use lighter liquid, because in that case we shall be getting the difference in the liquid level more if we are using lighter liquid for small pressure difference. Now let us look at how a U-tube manometer looks like. Here it is that we have a U-tube manometer. It looks like U, so that is why the name U-tube. So in this case we find there are two limbs, and these two limbs are placed in the pipeline where we want to measure the pressure difference. In this figure we find that the flow is taking place from left to right. So we have in this manometer some manometric fluid, that is liquid, and some process fluid which is also passing through the pipeline. And the two ends of the manometer are put on the one on the upstream side and one on the downstream side. And what we find, because the pressure on the upstream side is more than the pressure at the downstream side, we find that this liquid is pushed downwards more than the other limb. So we find there is a difference in the heights of the manometric liquid in the two limbs, and obviously when there is no flow through the pipeline, these two limbs will be having the same liquid heights. So here we see that the difference in the heights between the two limbs is h. Now we shall see that how we can find out the pressure drop using this U-tube manometer. So here we are showing that some datum B across which we are taking the force balance. So we shall be looking at the force acting on this plane B prime, and here we see that here this FB is the force which is acting on this limb, and FB prime is acting on the other limb, the downstream limb. So here we have the two forces have to be balanced, and when we are balancing the forces for this FB, what is happening? The force is due to this pressure P1 plus due to the hydrostatic height of this particular fluid. So we are writing P1 into A, that is the force, plus rho F G into HB into A. So this is the total height HB, that HB into A is the rho F A G HB into A is the force due to this particular process fluid. And on the right hand side we have plus P2 into A due to the flowing liquid. Then we have this small height, that is HB minus H into rho F into G plus this HB or H into rho M into G into A. So this is how we are getting the various forces which are acting on this plane B prime. Now after that, this force balance, we now make all these mathematical manipulations to ultimately get this particular equation which gives us the pressure difference between the upstream and downstream side in terms of the density difference between the manometric liquid and the process fluid and the height difference in the liquid column inside the U-tube manometer. So, once we know H, once we know this density of the manometric liquid and density of the process fluid, we can find out the pressure difference between the upstream and the downstream of the flowing fluid. After learning about the method to find out the pressure difference, now let us look at the various desirable properties which a manometric liquid should have. Based on these desirable properties, we can choose the appropriate manometric liquid for a given application. Here first is that the immiscibility with the process fluid. That means the manometric liquid should not be soluble in the process fluid. Then it should have high chemical stability, it should not get dissociated or it should not react with any other components with the process fluid or with the surrounding gases. So, it should be chemically stable. Then it should have low viscosity so that it can move in the manometric limbs very easily. It should not be needing the pressure energy from externally. Otherwise, we cannot measure the pressure drops properly. Then it should have low capillary constant. It's also related to its free movement through the manometric limbs. Then we have low a coefficient of thermal expansion, means in the range of the operation that with temperature it should not expand or contract too much. If it expands and contracts, its density will change. So, we will not be getting the right value or we have to keep on applying some correction for the densities if it expands or contracts. Then it should have low volatility. It should not, if it is highly volatile, then what will happen? It will evaporate. It will not be able to stay in the manometric limbs. So, we want that this should not have high volatility. And also to have low volatility, low evaporation, it should have a low vapor pressure, because high vapor pressure leads to high rate of evaporation. Now, let us see what are the advantages and disadvantages of the U-tube manometer. In the advantages, we have that it is quite simple in its construction, it is also not very costly, and it is fairly accurate and sensitive to the pressure changes. However, the disadvantages are that it is quite fragile, because most of the times it is made from glass so that we can see through it. So, it is fragile and it is also sensitive to temperature changes due to the change in the fluid density. Now, next we come to pressure transducers. Now, what are pressure transducers? They are some devices which work by converting the pressure change either into some mechanical displacement or some electrical signal. Now, when the pressure change causes some mechanical displacement, we call it mechanical transducer, and if the pressure change causes some kind of change in the electrical signal, maybe in terms of the voltage or the current, we call it electrical transducer. So, here we have two types of transducers, mechanical and electrical. First, let us go to mechanical transducer. Again, we shall be confining ourselves to a very few mechanical transducers. In this particular mechanical transducers, what we have some force summing device. That means it will be taking all kinds of forces which are acting on the device, that will be converted to some kind of displacement through some mechanical link to transmit and amplify the displacement. Then the advantages are that these mechanical transducers are quite simple in the construction and quite robust and rugged, and they are cheaper than the electrical transducer, can operate without any external power supplies. In some transducers we need some external power supplies like electric current to operate them, but in this case we do not need any kind of external power supply. Then they are capable of transmitting the mechanical signal over a reasonable distance. That means they need not be fixed right at the place where we are staying. We can observe them from a faraway place also, and then they can withstand high pressures and only react to difference between the two applied pressures. And coming to disadvantages of these mechanical transducers, they have poor frequency response. That means they are having some kind of inertia in when the pressure fluctuates too much, so they cannot sense the pressure properly if there is a lot of fluctuation, and they require quite large forces to overcome some mechanical friction in the instrument, and they are incompatible when remote control or indication is required. There are various types of mechanical pressure transducers. We are just listing only two of them. One is the Bourdon tube, which is very common and which is also found in our laboratory or in the industries quite commonly, and we have diaphragm. So let us first look into the Bourdon tube mechanical pressure transducer. In this Bourdon tube, what we have, that as we see in this particular figure, we have the Bourdon tube is a particular tube. This tube is there. This tube has elliptical cross section and is fixed at one end, and from this fixed end it receives the pressure signal. The other end is free to move and it is closed. So the other end is closed and the one end is open and fixed, other end is free and closed. And what happens when this pressure is sensed? This particular tube tends to stretch out or becomes more circular. So when it starts to stretch out, what happens on the other end? From the other end, through a pinion connection, there is a pointer is there, and this pointer will change its position as per the expansion of the Bourdon tube, and this pointer spans over the particular calibrated scale. And here in this particular figure we see that how the pressure at the inlet pressure will stretch this Bourdon tube, and how the pointer is going to move on a pre-calibrated scale due to some pressure change at this end. So this is how a C-type Bourdon tube works, and there are many other type of Bourdon gauges. We are just looking at a typical Bourdon gauge. Then we have another type of mechanical pressure transducer, that is the diaphragm type. Now in this diaphragm type, what we have, that here we have a diaphragm. So here we have a diaphragm, and there is again, like the Bourdon gauge, we have another pointer here. So how it works, that whenever there is a pressure on the diaphragm, this pressure through the pinion arrangement, this will again cause a movement to this pointer. So depending on the pressure coming to the diaphragm, this pointer will move on the left hand side or the right hand side. So this is how the diaphragm pressure gauge works. Now let us make a quick comparison of the Bourdon tube with the diaphragm pressure gauge. Here we see that the Bourdon gauge can go for a higher pressure range, about 1 atmosphere to about 1300 atmosphere, and then but while the diaphragm gauge goes for a lower pressure range, we can see it go up to millibar pressure range. Then if we want to measure low pressure, we will go for the diaphragm type, and this Bourdon gauge can operate in corrosive environment, whereas diaphragm is not suitable for corrosive environment. Next we come to electrical pressure transducer. In this, the pressure sensed is converted into some kind of electric signal, either in terms of current or voltage or some frequency. Now what are the advantages and disadvantages? Let us see that advantage is they are better than the other gauges and mechanical transducer for remote reading or for automatic control or for signal processing. That means if we want to have some automation in the industry, we cannot use the mechanical transducers. We have to go for the electrical transducer, because with them only we can capture the data, and also whatever control actions or automations have to be done, we can transmit those signals from the electrical transducer to our control room, which is not possible for the mechanical transducer. And the delay in the response is also eliminated, almost eliminated, because it is electric signal. So there is the response time is very small. So these are the advantages of the electrical pressure transducer. However, the disadvantage is that basically they are quite expensive. Next we come to the various types of these electric transducer. First we have the strain gauge. In the strain gauge, what it says that it works on the straining, that is the deformation of some element. Here we show the strain gauge type. What we find in this figure is that we have a diaphragm, and then we have this cross shaped spring, and then we have some rods over here which will be displaced, and we have the strain gauge windings. So these are the basic components of a particular strain gauge: diaphragm, then cross shaped spring, then these rods and the strain gauge windings. Now how it works? Let us see that suppose from the diaphragm side we are imposing some pressure. Now because of this pressure, what will happen? It will push this particular cross shaped spring downwards, and when it is pushed down, what will happen? These rods will be tilting inward at the top, and they will be going towards the outward at the bottom side. And when these rods are getting tilted, what will happen? They will also, these strain gauges will also be getting some displacement, and because of this, resistance will change, and this will send the signal to some appropriate signal data logger. So what will happen? This resistance change is related to the strain by some quantity known as the gauge factor. And what is gauge factor? Gauge factor is defined like this. It is the ratio of the relative change in the electrical resistance to the mechanical strain. That means this delta R is the change in the resistance due to the deformation or the tilting of these rods, and this is the original resistance, and this is the actual strain that has taken place. So with this gauge factor, we can know that what is the actual pressure that has been imposed by some calibration. Now the advantages of this kind of strain gauges are that they are quite fast in response, and they are simple to maintain, and their sizes are small, and they can be installed easily. On the other hand, we have the disadvantage as that they have the span or the range of pressure they can measure is small. Next we go to the load cell. In this load cell, we find that the operating principle is similar to that of the strain gauges, and first let us see the advantages, that they are easily available and they have quite high accuracy, which is about even less than 0.1% of the full scale accuracy may be obtained. They can be calibrated easily by the manufacturers or vendors. On the other hand, they are quite bulky and they are quite rigid. That means we don't have much flexibility in their installation, and they require quite expensive electronics. Now there are various types of load cells available commercially: strain gauge, piezoelectric, hydraulic load cell, pneumatic, but essentially their working principles are almost same. So we shall be looking into only this strain gauge load cell. Here we find that how it works, that first we see this construction. In the construction we see that there is a metallic cylinder with some flange base plate, and on this particular cylinder we are having 4 resistances. There 2 resistances are placed horizontally, and 2 resistances, we are showing one resistance over here, there is another resistance on the opposite side. So there are 2 resistances which are arranged horizontally, and 2 resistors are arranged vertically. So here in this top view we can see that these R3 and R1 are horizontally and R4, R1 are vertically. Now what happens that whenever we are imposing some kind of a pressure on the top of the cylinder, this particular cylinder barrel tends to deform, okay, and this cylinder means we are deforming it, it's trying to bulge out. So when it starts to bulge out, what happens? These resistors change their positions and their resistances change, and this change in the resistance of the resistors are recorded and they are related to the pressure imposed by some kind of gauge factor, as we looked into the in kind of the load cells. So here we find that these strain gauges are working in a similar fashion as per the strain gauges. The load cell and strain gauges are similar in their functioning. Now we find these are the comparison of the mechanical and electrical pressure transducer. That accuracy wise we find that electrical transducer are giving higher accuracy than the mechanical transducers. Cost wise, of course, mechanical transducers are cheaper than the electrical transducers. The size wise also the electrical transducers are smaller than the mechanical transducers. Power requirement is higher for mechanical transducer because the pointer has to overcome some kind of frictional resistance, which is not the case with the electrical transducers. Then mechanical failure is more in case of the mechanical than for electrical transducers. On the other hand, for any kind of automation, control or signal processing, electrical transducers are preferred to the mechanical transducers. Now these are the references which you may refer to for further details. Before this, I would like to show you this. This is the thing. This is the pressure transducer. Here you can see there is a small hole over here, which this we put in the transfer line wherever there is some process fluid is passing, and on this particular hole this fluid pressure is exerted, and this particular portion is a transmitter portion through which this signal of the pressure is transmitted, and from here, from this particular port, we take the signal out, electrical signal from the particular transducer. So this is how a pressure transducer looks like, and here I show you the strain gauges which are very small. These are very small. Their strips are there, and these strips are pasted on wherever we want to measure the pressure drops, and these strips will change the resistance, and the resistance is measured appropriately to get the pressure drops. Thank you.